Hello, all. Good morning and welcome. It gives me great pleasure to introduce our speaker for today, Jesus Ortiz, who will be speaking on assessment of the development length equation for GFRP rebars in tension. Jesus is a PhD student in civil and architectural engineering at the University of Miami. He holds a BS and MS in civil engineering from, I will butcher this, I apologize in advance, University Escuela Colombiana de Ingeniería Julio Garavito in Colombia. His current research focuses on the application of FRP composites in reinforced and strengthened concrete structures, and also on non-destructive testing methods for inspection of FRP RSC elements. Thank you very much, Jesus, for agreeing to do this, and the floor is all yours.
Thank you, Dr. Suraneni. Good morning, everyone. I hope you are hearing me well. Thanks for the kind introduction. So it's a pleasure to be here today to talk to you about one of my students here as a PhD student under the advisor of Dr. Nani. So the title of today, as Dr. Suraneni mentioned, is Assessment of the Development Length Equation for GFRP Rebars in Tension. I know it's a long title, but don't worry, we will go together to understand the meaning of it. So let's get started. Okay, so first I want to show you one of the specimens we're testing right now and see if you can guess what type of failure it might be. So we got a single crack with multiple minor flexural cracks, and I hope you to try to guess what failure mode this big crack was. I have like around 40 minutes to explain you the importance of this crack and why this is not a desired failure mode. At the end of this presentation, I will show you the same video with some of the preliminary analysis along with its failure mode to see if you got it right. So here's the outline of the presentation. I will go over a brief introduction and background to highlight the problem, what we want to achieve with this research and how we are doing that, and what we have found so far is a research in progress. So first, explain some of you who may not be familiar with the term FRP. So FRP, it stands for fiber reinforced polymer, and it is a composite material. So it is made of a reinforcing phase, the fibers that are embedded or impregnated in a polymer matrix. So those fibers provide the strength and carry most of the applied load. They should be continuous fibers. And the resin or the polymer matrix binds them together, thus transferring the stresses and providing protection to the fibers. So what are the advantages of this new material? First, it is a non-corrosive material, so they have long-term durability compared to steel. They have a high longitudinal tensile strength, so if you think on a steel rebar, it has a yield strength of about 60 KSI, and an FRP GFRP bar could have a strength of up to around 200 KSI. Also, they're lightweight, so it's like around 1/5 of the steel weight. Low thermal and electrical conductivity for certain applications, but it also has some drawbacks. So first, it is elastic up to failure, so no yielding before failure. You don't have that ductility compared to the steel rebars, although in a reinforced concrete element, there could be some design approach to reach some ductility, but we don't go into detail. It has bigger deflection compared to steel because of its low modulus of elasticity. It cannot be bent in field. I put this sentence in italics because it's not 100% true anymore. There are some types of resin that allows bending in field. Also, it higher initial costs. That's also not always true, because it depends on the market. The initial cost of GFRP has changed significantly over the past 2 years. Also, the cost of or the fluctuation of the metal market worldwide has increased in the past the cost of the steel rebar. So it depends on the market, but has a lower long term because of the good durability. So you need less maintenance. Also, it has longer development length compared to steel rebars. So this can be an issue related to detailing and constructability. So in summary, there are different types of fibers and resin that you can use to manufacture FRP composites. You have continuous carbon, glass, fiber, basalt, aramid fibers, and you have two types of resins, the thermosetting, thermoplastic. The thermosetting, right now the ASTM to manufacture GFRP is the only available, the only that is permitted. To manufacture, also you need to, or usually the manufacturers include some additives and filler to the mix. And then you have the FRP composites. So you could have carbon, glass, basalt, or aramid, so CFRP, AFRP, BFRP. And with those composites, you could have different structural elements like GFRP bars, FRP strands, FRP meshes for internal applications, or plates, fabrics, near surface mounted bars for external applications. So from here on, I will be referring only to GFRP bars using as reinforcing materials in concrete structure, and we'll be addressing the long-term, the long development length disadvantages of these elements. So the flexural design philosophy of GFRP reinforced concrete element is somewhat analogous to those of steel reinforced concrete, with, of course, a specific variation because of the nature of the GFRP composites. Here are the 5 initial assumptions that you can find in the ACI code for 440, or also in the 318 for steel. First, plane sections remain plane after deformation, the same as steel. Ultimate concrete strain, usable concrete strain 0.003. The tensile strength of concrete and the FRP compressive strength, the strength are neglected. Here, you disregard the effect of the FRP rebar in compression. In steel, you can account for that. The FRP is perfectly bonded to the concrete, and stress strain of FRP is linear until failure. The previously mentioned development length is closely related to the fourth assumption. In order to be able to assume a perfect bonded behavior, you must fulfill the development length requirements. You must have that minimum length in order to assume that you have a perfectly bonded concrete to the FRP rebar. But what could happen if you don't fulfill these requirements? So, well, your beam element is more likely to present a bond failure. Bond failure means loss in tensile or compressive force in rebar. Here, we're only going to focus on tensile forces, and that will result in element failure. So imagine that you have a rebar embedded inside a concrete block, and you try to pull it out. If the embedded length, the length that you put inside the concrete, is long enough, you are going to break the bar. That's what usually we want. But of course, assuming that we are avoiding other types of failure like concrete crushing or other types of failures. If now you reduce that length and you try to pull out the bar, you are going to pull it out and you will have a bond failure. That is usually referenced as pull-out failure or slippage failure. The bar is slipping from the concrete. This can be avoided by either mechanical and anchorage or sufficient embedment of the rebar. For FRP, the second one is the most used, even for steel one, but you could have some types of mechanical anchorage at the end of the rebar. So we have talked about embedment length and development length, but what is the difference or the relation between those two words? So the ACI defines the development length as the length of embedded reinforcement required to develop the design strength of that reinforcement at critical sections. So in other words, is the minimum length of reinforcement bar that must be embedded in concrete to ensure adequate anchorage and transfer those tension forces. If you have embedded, if you need to embed your bar or you need to splice your bars because you need to cut it and you need to splice those bars, is that minimum length that you need to transfer those stresses. So these tensile forces are transmitted to the concrete by means of the bone stresses. The bone stress varies as the moment varies, depending on the cracks, depends if you change the tensile stresses on the rebar. So if we imagine that we have this beam, this concrete beam, simply supported, it's cracked, it's already cracked, and we made a cut on a crack section next to an uncracked section. So if we have a crack beam subjected like this stress diagram, in the uncracked section, the concrete tension is taking some of the tensile stresses, but of course, in the crack section, you already lost that tensile capacity of the concrete. If we draw the free body diagram of the bar, we will have different tensile forces that it is equilibrated by the bone stresses, because here the concrete is helping the tension, the tensile stresses. Here the bar is taking the full stresses. So there are like an incompatibility of forces there that should be taken by the bone stresses. In this diagram, I'm representing the bone stresses with blue arrows of the same size, assuming a constant bone stresses, but in reality you have multiple cracks along the length of the rebar, and the distribution of bone stresses is complex to determine because you have multiple cracks. So in those cracks, the bar must take the full capacity, the full stresses, but once you start to move away from that crack, those stresses are being transferred to the concrete. So it's what usually is referenced as in and out bone stresses. So the distribution is not uniform, although usually when we are addressing the bone stresses, we assume a constant and average distribution of those stresses to simplify some of the calculus. So there are different ways to determine the bond quality of rebars to concrete. So you could run some different tests, pull-out tests, embedded rod tests, or beam tests. The pull-out tests are the simplest, but they are typically only used to compare the bond efficiency because the concrete is always in compression. You don't have any cracks, so it's not the reality what you usually have in a beam. Additionally, for FRP rebars, we don't have a standard surface treatment like for steel that we have always those ribs, and those are standardized for the ASTM in the ASTM specification. But for FRP, you could have different types of surface treatments. So to summarize the four categories, we could have sun-coated FRP, we could have groove, ribbed, or helical wrap surface treatments, and even we could have a mix of them. So we could have a sun-coated rebar plus helically wrapped. So it depends on the manufacturer. But those bone stresses depends typically on chemical adhesion, friction, and bearing of the reinforcement to the concrete. In a steel, the bearing capacity is the most important because, of course, you have a good ribs there in the steel. But in the FRP, if you don't have ribs, if it is uncoated, so the friction maybe could have more relevance there. So bond failure modes are not only characterized by pull-out or slippage failure, but because beams in flexure also could have a bond failure that is named splitting failure. That depends on different parameters like the bottom side concrete cover, the distance between the longitudinal rebars, the compressive concrete strength, the embedded length, the rebar diameter, the confinement because of the transverse reinforcement. So it's a more complex type of failure. If we focus on a steel rebar, that is maybe easier to see because of the ribs. In a steel, this effect is called wedging action. That is when the pressure of the ribs against the concrete produce tensile forces. So the concrete start to cracks. So if these cracks extend to the full bar length, you are going to have horizontal cracks and you are going to lose that concrete cover. If you lose that concrete cover, you are not be able to transfer those stresses to the concrete and vice versa. So you are going to lose the capacity of your beam. So this is another type of failure. So bond failure modes, we could categorize them between a pull-out or a slippage failure and a splitting failure. What do we want? Usually we want to have the tensile failure. We want to break the bar, assume that the bar is well anchored in the concrete, so we can break the bar. How the current design codes and guidelines address this problem? Specifically for GFRP, the ACI 440 code works with an equation that was developed in 2006, and it was based on 240 beam bone tests. So there are different test setups to evaluate those bone, different beam tests that we can use to evaluate that bone distribution. And the methodology to develop that equation was similar to that of established in ACI 318 for steel. This equation was developed based on a 2-parameter linear regression, same as the one established in 318 for steel. They only use the result from literature review that resulted in splitting failure. So this equation here that includes some of the already mentioned parameters already mentioned, like the concrete cover, the bar diameter, the embedded length, the concrete compressive strength. This U is the bone stresses, the one that we want to analyze. This equation is only for a splitting failure. The pull-out failure or the slippage failure is usually avoided by putting a minimum limit on the development length that is around 12 inches or 20 times the bar diameter. So with that minimum required length, you avoid the pull-out failure, but the splitting failure is a little bit more complex. So this equation was based on test data conducted over 2 decades ago using a bar with surface deformation, either helical wrap or rivet treatment. Now we have more surface treatment. Some conservative assumptions were made due to the lack of available data at the moment. Now we have more data, and some parameters were disregarded. If we compare it with the one for steel, that includes the effect of the confinement, the transverse stirrups. For GFRP, we're not considered that effect. And there have been significant improvements in FRP material properties. Now we have the second generation of FRP bars, better properties, better qualities of the rebars. So there is another reason to reassess this equation and see if we can improve that equation. So if you solve for the embedment length in the previous equation, and after some modification to include safety factors, strength factors, you will get this expression on the right side that is available in the ACI 440 code. I'm not going to go into detail on each parameter, but you can see the difference in the equation when compared to that of a steel. Both equations include some coefficients. Here in the GFRP, we have less coefficient than in the steel, that are coefficients for if it is an epoxy bar, if you have the grade of the bar, if it is a 60 KSI, 100 KSI, but there are coefficients so multiplied by 1.2. So these both equations were developed based on a statistical approach and not a mechanical one. So that's the reason why the equation do not seem to have like a physical meaning. So like why you are subtracting by 340. So it's because it's what, when they plot the data results, is what the equation that better fit those data. So it doesn't have like a physical meaning behind that. Okay, so this is the graphical abstract of the research we are currently carrying out. We decided to test 38 concrete beams on this first phase. The beams are 300 millimeters wide by 450 millimeters deep and 5.2 meters long. The parameters that we selected were based on the literature review that could influence that bone strength, so the concrete compressive strength, the GFRP bar diameter. For this phase, we are only focusing on number 5 GFRP bars. The concrete cover, clear concrete cover. So here, some people think that because the GFRP or the FRP bars don't have those durability issues or corrosion issues, you will need less clear cover. But the clear cover or the concrete cover is not only for durability, but also for bone and to fulfill those assumptions or those requirements. Also, we are including the confinement effect and of course the splice length. We have different length. We are recollecting some data, information about the structural performance. So we have LVDTs to measure the mid-span deflection and deflection at different points. We have some potentiometers installed inside of the rebar. I'll show you how we did that. Of course, we are classifying in the different failure modes that I already show you: splitting or splitting, slippage or pull-out failures, rupture, concrete crushing, those types of failure modes. We have also strain gauges on the concrete, on the surface of the concrete and inside in the rebars. And of course, the load that we are recording and we are applying. So once we finish recollecting all this data, the next phase, and the one that we're currently working on, is the data processing. So analysis of all this data. So plot this data, understand the structural behavior of those elements, what happened when we change those parameters. So it's the phase that we are currently working on. So here is an illustration of the beam specimens we are testing in the lab. We divided them into phase 1 and phase 2. Phase 1 only have one rebar with different covers, as the one that you are seeing. Phase 2 have two rebars with confinement effects. So that means that we have stirrups also in the middle. This is a 4-point bending test. So we have constant moment in the middle part of the between the points of application of load. So regarding the splice length, we are currently evaluating 3 different lengths: 40, 60, and 80 times the bar diameter. The first phase is only focused on number 5 rebars. So if you compute the required development length based on the ACI for 4 equation, you got 110 times the bar diameter. So it's around 1.7 meters. So imagine if you need to splice those 2 bars in a beam, you will need almost 2 meters available to splice that, or if you need to embed that bar to anchorage at the end of the rebar or to a column, you will need that length or that space to anchorage and fulfill with this requirement. So we have 40 dB, we are analyzing 60 dB and 80 dB. So what happened when we increase those development length, how the bone stresses are being transferred to the concrete. So for the instrumentation, we install strain gauges in the rebar, so at different locations. Later, strain gauges also in the concrete were installed. We have LVDTs in different points to generate that first crack at the exact end of the splice. We notch the beams at this point. So here we have a notch at the end of the splice. So we are forcing the location of the first crack. We know that the first crack is always going to appear at that point, although without the notch, the first crack could have appeared also close to that location. We want to force the location at a point that we already know. Additionally, we install a small potentiometer in the rebar to measure the slip, to know if the bar was moving. So the procedure was simple but efficient. We drill a hole in the center of the bar with enough tolerance to embed the shaft of the potentiometer. Before embedding the shaft, we apply some resin to ensure a good adherence. And then the potentiometer was covered with a heat shrink tube in order to avoid any damage when pouring the concrete and ensure that the potentiometer wouldn't move. From the result that we have got so far, we saw that this potentiometer was recording. It didn't move from the concrete. So here is a short video of the specimen fabrication. All this fabrication and test is being conducted in the University of Sherbrooke in Canada. Something to highlight is that I was able to move those FRP cages around by myself. But once we had some steel bars, I needed extra help to move them. So one of the advantages already mentioned is the lightweight. So here I evidenced that by myself when trying to move those cages around. Here, extra videos of the concrete pouring and the making of the notches. There you can see the strain gauges cables. We try to be very careful with the tape to not break the bond between the bar to the concrete, because of course when we tape the rebar, we are breaking that bond. So we try to be very careful and to try to, if we are breaking the bond, that will be the less amount possible. Here, this video on the right is the notch. It's less than one inch notch to generate and for that first crack on those locations. Okay, so we prepared the loading protocol. It was a displacement loading protocol. We have 3 cycles. The first one is up to the cracking moment. The second one up to the design load. What is the design load? Is that one that you get with the equation of the ACI 440 with all the safety and strength factors, or if the bar moved, so we also unload at that point of a slip of the rebar. And then we go up until failure. So we start testing. Here is the video I showed you at the beginning of the presentation. It is a phase 2 beam, meaning that we have a splice length of 40 times the bar diameter. We have stirrups every 4 inches. And on the right part here, you can see the applied force versus mid-span deflection. So how what was the structural behavior of the element. And of course, a picture after the test. I put that red line to reference to see the deflection of the rebar, of the beam, sorry. And once the beam was tested, we analyzed its failure, and we conclude that this is a clearly bone failure, specifically a slippage failure. Why a slippage failure and not a splitting failure? Well, it's a slippage failure because the bar didn't break, so it wasn't a rupture of the rebar. The concrete didn't crush, so it wasn't a concrete crushing failure. And additionally, we don't have any horizontal cracks, so it wasn't because we lose that concrete cover, but because the rebar slips from the concrete. And later, when we analyze the potentiometer, we also saw this behavior. So here is another specimen. This is from this time. We have a longer length, 60 dB, without confinement. And here, you can see the brittle and sudden failure. With, of course, it was a big damage, but you can see that crack or horizontal crack between the 2 main cracks. So of course, we classify this as a splitting failure, and you now know what we have to put that mesh there for safety. Here is another specimen where you can see more clearly the horizontal cracks and the loss of concrete cover in this part. So it was a splitting failure. This beam was the reference one. It was a continuous rebar with no confinement. So in this case, the expected failure mode was concrete crushing. So we classify this as, of course, concrete crushing. The rebar didn't break. And of course, here, we didn't have any slippage or splitting. Finally, one of the reference specimens, the beam with the steel rebars, where we have the steel yielding failure mode. In reality, it didn't fail. I mean, the rebar didn't break, but we have large deflection. So we stopped the test after large deflection after around 3 hours. So we say, okay, the steel is going to continue yielding. So it's okay, we can stop it and classify as steel yielding. So here's some preliminary results of the beams we have tested and analyzed. In the graph on your left, you can see all the specimens with 40 dB of splice length. The black one is the reference one, and it is clear the contribution of the stirrups. The blue one with the triangles is the specimen with the stirrups every 4 inches. The green one is the stirrups every 8 inches, and the red one is without any stirrups, so we don't have any confinement. So here we can see that even though the ACI for equation does not include the effect and the contribution of the stirrups, we see that when we have stirrups and the separation of the stirrups are helping with the capacity of the beam. Also, here I highlight the design force. So if you try to design that beam with those reinforcement ratio with those dimensions, you will get a design force of around 130 kilonewtons with all the safety factors in the ACI. So the beam without confinement and 40 dB of a splice length was the only one that was below that limit. And the expected force, we have a good prediction. The expected force was for the continuous beam, so it was almost 99%. On the right side, there is the same graph, but only for 60 dB. So here also we can check the contribution of the stirrups and also the difference and the contribution of a longer splice length. Here, the specimen with stirrups every 4 inches got almost 230 kilonewtons. Here, the specimen with 4 inches was less than the capacity of the one with 60 dB. Another graph, you can see all the specimens from phase 2 without any confinement. So again, the contribution of the splice length we can notice here. And also you can observe that only the 40 dB specimen, which capacity is lower than the expected by design, but even the 60 and 80 that was, if you remember, the required by ACI was 110. We got capacities larger than the design force or design moment that you were expecting. Another comparison with the steel specimen for you to see the difference on behavior between FRP concrete and steel concrete. You can observe the 3 typical stages in the steel specimen. So here, of course, the steel start yielding. So we start that plastic behavior. And the contribution of stirrups in the steel specimen seems to be irrelevant. Here, it's also because we stopped the test here, but it could keep yielding. So here we can check that the orange one has stirrups every 4 inches. This pink one doesn't have any confinement. But when you compute the development length, the required development length for steel, it's around 20 dB. So we are putting 40 dB. Of course, it's larger than the one that is required. It doesn't have any contribution to that. Also, you can check the difference between the structural behavior at the same load. Here we have only a deflection of around 18 millimeters, but the one of FRP has around 55 millimeters of deflection. So we have more deflection because of the low modulus of elasticity, but the final capacity is way larger than the previous one. So what we want to do with this data that we have collected so far, so where we are right now, we are constantly analyzing and recollected all the data. We have more than 30 beams that we are analyzing right now with different behaviors, with different failure modes. We are focusing on understand the structural behavior and how the stresses were transferred along the length of the rebar. So for doing this, we are mapping the cracks to observe the crack pattern and the required length to transfer those stresses. So we know that the first crack is at the notches because we are forcing that first crack, but we are studying and analyzing where is the second crack, what is the distance between that first crack and the length between that first crack and the second crack, how much stress were transferred between those 2 points, and then you have another crack. Was that length enough to transfer those stresses to try to understand the behavior and the way that those bone stresses are being transferred between the rebars to the concrete and between those rebar that we have spliced there. Of course, we have the strain gauges inside the rebar that we also are analyzing, the potentiometers, the strain gauges in the concrete. So we have plenty of data that we need to understand, and we need to see how they are related with each other. So I hope we can soon present the final conclusions and results of this study. This is from phase 2, so we have different data. The equation of the ACI, it could have some, we could reassess that equation with the result we have gotten so far. Of course, we also have results from the literature review that we have analyzed. So the idea is to have a similar procedure that they did for when they computed the first equation around 20 years ago. So, but with new data, with new materials, with new properties, with the better properties of the rebars to try to reassess that equation. So I hope we can soon present the final conclusions and the results of this study. Finally, I would like to acknowledge the research group behind this project. This is a joint project between the University of Miami and the University of Sherbrooke in Canada. So a special thanks to the technicians at Sherbrooke that who have supported and assisted us throughout the project. Dr. Nani, of course, and Dr. Belmore Crane in Sherbrooke were the professors that are helping us on this research. So thank you everyone for listening to me these 40 minutes. I think we did it on time. And I hope you found this interesting this presentation. And if you have any questions, I'll be happy to respond to them.